Hello. Today we are going to see the lecture 5 of the unit 3, that is spherical polar coordinates. We learned so far the double integration, evaluation of double integration, change of order of integration, evaluation of triple integrals, evaluation of double and triple integrals by change of variables, in particular change of variables in case of double integrals in polar coordinates, in case of triple integrals to cylindrical polar coordinates. In today's lecture, we are going to learn how to evaluate triple integrals while changing to spherical polar coordinates. So change of variables to spherical polar coordinates. So before knowing how to evaluate a triple integral by changing to spherical polar coordinate, first of all, let us know what actually the spherical polar coordinates are. In 2 dimensions, we have two methods of identifying a point or the curves on the plane. They are one is Cartesian coordinates, another is the polar coordinates. Similarly, in 3 dimensions, we have three systems. One is Cartesian coordinate system, another one is a cylindrical polar coordinate system, and the third one is a spherical polar coordinate system. In Cartesian coordinate system, the references are the three planes, xy plane, yz plane, and zx plane. Those are the three planes are the references. If you have any point in space, that will be identified by the distances from these three planes, and depending and every distance is associated with a sign depending on which side that point is to the particular plane you are considering. In cylindrical polar coordinates, we have the references as one is the origin, another is the z-axis, another one is the polar axis. Those three are the uh, references. If you take a point in space, at that point from the origin, it will have some distance. That distance will not be considered there in cylindrical polar coordinates. Take that point P in take the projection of P on the xy plane. Let it be something like Q. OQ is R, and that OQ makes an angle theta with the x-axis. The polar coordinates in a plane and the z coordinate from the Cartesian plane, those two put together gives the cylindrical polar coordinates. We discussed about that in the previous lecture. In this lecture, spherical polar coordinates. This is in the spherical polar coordinates. They determine the position of a point in space or in three-dimensional space based on a distance and two angles. The let us suppose that point P is at a distance from the origin. R be the distance of that point from the origin. Let something like say L, I'll call L be the okay, I used here L, here also L is. Let L be the projection of this point P on the xy plane. Now this radius vector OL will make set an angle phi with the x-axis, and this OP will make some angle theta with the z-axis. So if some other point is given here, this will have different projection, and from origin to that projected point, if this point is P dash, L dash is this. This is the distance from origin to that P dash is that length, and this OL dash makes an angle phi 1 with the x-axis, and this OP makes an angle theta 1 with the z-axis. Then R1, theta 1, phi 1 will be the coordinates of this point. So generally, this is the standard notation, is the internationally followed notation. The middle one, the theta, will always be the angle made by this OP with the z-axis, and the last angle is the angle made by the projection vector of OP on the xy plane, that is OL, with the x-axis. So these are this angle theta is called the polar angle. So the radial distance is known as this OP is known as the radius or radial coordinate. This is called the radial coordinate. R is radial coordinate. The polar angle theta, this angle theta is called the polar angle or co-latitude angle or zenith angle. These are different names generally used. Normal angle or inclination angle. Several angles we have. And this angle phi is called azimuthal angle. So if I say a point P is something like 2 pi by 6 and pi by 4, this means in the space there is a point P which is at a distance of 2 units from the origin and which makes an angle pi by 6 with the z-axis, and the projection of that P on the xy plane, if I call it as Q or L, whatever it is, that OQ makes an angle pi by 4 with the x-axis. That's what it means. So this is how in spherical polar coordinates we determine a point. So this spherical polar coordinates is very convenient method, especially in 3 dimensions, to evaluate triple integrals. So we have Cartesian coordinate system and spherical polar coordinate system. Let us know the relationship between Cartesian coordinate system and spherical polar coordinate system. So if this is the point P and this is L, From this, if I draw a perpendicular on the y-axis as well as on the x-axis, that means this is at 90 degrees, this is also 90 degrees. And here from P on z-axis also you write one perpendicular from P on the z-axis. So this is also right angle. Yes, because this is right angle and this length we know that it is R, and from this right angle triangle, 1, I can find out the sine theta. The sine theta is this length Pz by R, then that Pz is R sine theta. Therefore, this length is R sine theta. This and this both are same. If you observe, this is a parallelogram, these two are parallel. Of course, these two are same. Whenever this is same, this length is also r sine theta. So this is what in this figure I mentioned all those things. PL is this perpendicular, this is right angle, this is right angle, and you write this is also right angle. So sine theta, this length is P is equal to r sine theta. That is how we get P is r sine theta. Because this is a right angle triangle, because opposite to right angle is this, therefore this becomes the hypotenuse. And from this, if I can find out sine phi, cos phi, I can find out. Why I am finding sine phi and cos phi? If this point is r theta phi in Cartesian coordinates, if it is x, y, z, you know that from this length is your z. This is the z code. This is your z, and from this point P, the from the xz plane, the perpendicular distance from xz plane is the y coordinate. Therefore, this length is your y. The projection of this point on the yz plane is your x. Therefore, this is your x. Actually, this is also your x. This is x. This is y. So because this is x and this is also x, this is also x. So from this, this is x, this is y, and this is your z. So from the same triangle 1, right angle triangle 1, if by finding sine theta, I got this length. And if I apply cos theta, I will get this length. This length and this length are same. So cos theta is this by hypotenuse, therefore this is r cos theta, this is r cos theta. Therefore this is also r cos theta. So one relation, this in Cartesian coordinates, this length is z, but in that is equal to r cos theta. Now from this triangle I'll call it as 2, from this triangle 2, find sin phi. Sin phi is this by hypotenuse. Hypotenuse is r sin theta. Therefore, y is hypotenuse into sin phi. So this y is hypotenuse. Hypotenuse is r sin theta into sin phi. So here r sin theta into sin phi. And similarly, if I find cos phi, you will get x. X is cos phi is x by r sin theta. X is r sin theta into cos phi. So x is r sin theta into cos phi. Z is r cos theta. Therefore, the the relation between Cartesian coordinates and spherical polar coordinates are given by this. X is r cos theta sin phi, y is r sin theta sin phi, z is r cos theta. I mentioned the internationally standard method is the mid one. We always represent the angle made by this OP with z-axis. So just to remember, z is equal to r. With that angle only, z will be given in terms of that angle. Z is r cos theta, x is r sin theta, y is r sin theta, cos phi and sin phi. We have to multiply with cos phi and sin phi. Okay. So to remember that easily, how to write the Cartesian to coordinate? Suppose if I say so the say rho alpha beta are the uh, spherical polar coordinates. If I say, it means the middle one is making an angle of alpha with this point with this OP. This is my alpha, this is my rho, and if I draw a perpendicular onto the xy plane, and if it is Q, this OQ is making an angle. This is x-axis, this is y-axis, and making an angle beta with this. And to write the uh, relationship between Cartesian coordinates to spherical polar coordinates, always because this is alpha, you write it is rho cos alpha, and the same rho sin alpha right here for. And in general, in polar coordinates, x is equal to r cos theta, y is r sin theta. Always we write x cos first and next sin. Therefore, for the other angle, you write here cos beta and sin beta. This is x is equal to rho sin alpha cos beta, x is equal to rho cos beta, rho sin beta, rho cos alpha. Or this other way also you can easily remember. Like this is beta is the angle in the xy plane. In a plane, if you have the angle in polar coordinates, then I always will have x is equal to r cos alpha, r cos beta, y is r sin beta. This is what we learned in your polar coordinates. And because that z is angle made with alpha, then you write rho cos alpha. And in these two places, you write sin alpha. In this way also you can remember. So whatever angle is given, if somebody says r phi theta is the spherical polar coordinates, if they give, always remember the middle one is the angle made with z-axis. In this case, the relationship is x, y, z are given by x is r cos theta, y is r sin theta, z is r cos phi, and you write here sin phi. So by looking at this, you should be able to say what are the polar coordinates. If somebody writes x is equal to r cos alpha cos p sin q, y is equal to r sin p sin q, z is equal to r cos q. If I write, then the polar coordinates are r, q, p. So whatever angle you have written here, that will come as the middle, and the same angle in these two you will get for sine q you will have, and this p is cos p and sin p you will get it. So this is how we will write the Cartesian coordinate. This is the relationship between Cartesian coordinates and spherical polar coordinates. So ultimately, if p r theta phi are the spherical polar coordinates of a point, and x, y, z are the Cartesian coordinates of the same point, the relationship is x is r cos alpha sin theta, y is r sin phi sin theta, z is r cos theta. This is polar to Cartesian. So once polar are given, you can find out the Cartesian coordinates. Reverse. So what is the reverse? That reverse in the sense from Cartesian to polar. It means if Cartesian coordinates are given, how to find out the polar coordinates. Now you add all the three, square and add them. X square plus y square plus z square is, if I square these two, r square sin square theta is common, cos square phi plus sin square phi is 1. And if I square this and if I add, r square can be taken common, cos square theta plus sin square theta is 1. X square plus y square plus z square is r square. That means r is root over x square plus y square plus z square. What is theta? Theta you can easily find out from this. This theta is z by r. R is root over x square plus y square plus z square. And phi, how can you find phi? If I divide one by the other, sin theta gets cancelled. Sin phi by cos phi, r also gets cancelled. Tan phi I'll get. Phi is tan inverse y by x. So if these are the relationship, if x, y, z are known, and if you want anywhere r, theta and phi, this is the relationship. This is the relation Cartesian to polar. This is polar to Cartesian. This is how we remember the polar coordinates. So we learned what actually the polar coordinates are, spherical polar coordinates are. So once you know spherical polar coordinates, and let us apply that spherical polar coordinates in evaluation of triple integrals. If Cartesian in a Cartesian coordinate system, if you are given a triple integral, to convert that into spherical polar coordinates, we need to substitute in place of x r cos phi sin theta, r sin phi sin theta, and z is equal to r cos theta. These are the things what I need to substitute. And we learned in the lecture 3 that whenever you take a transformation, to replace dx, dy, dz is to be replaced with Jacobian times dr, d theta, d phi. So let us find out the Jacobian. So Jacobian of xyz with respect to r theta phi. So in the first row, what is that you'll have? Derivative of x with respect to the three variables r, theta, and phi. The derivative of r with derivative of x with respect to r is cos phi sin theta. Derivative of x with respect to theta is r cos phi cos theta. Derivative of sin theta is cos theta. Derivative of this with respect to phi is minus r sin phi sin theta. Derivative of cos phi is minus. Similarly, derivative of y with respect to r theta phi will be written in the second row. The third row, if I find the derivative of z with respect to r and theta, dou z by dou r is cos theta, dou z by dou theta is minus r sin theta, there is no phi, therefore dou z by dou phi is 0. I need to evaluate this this determinant. So in the second row, second column, r is common. The third column also r is common. So r is I have taken from these two columns, therefore r square will be there. And here sin theta is there. So sin theta also I have taken common. So if I take these two, and the remaining part will be cos phi sin theta, r I have taken cos phi cos theta, r sin theta I have taken common minus sin phi. Similarly, this sin phi sin theta, from here I have taken r common, therefore remaining is sin phi cos theta. From this I have taken r sin theta common, cos phi I have written. From the last row, cos theta is there. In the second column, I have taken r common, therefore minus sin theta is remained. I need to evaluate this determinant. So this is r, this determinant is cos, I am expanding this with respect to the last row, cos theta into, I'll remove this one and this minus this. If I multiply this to cos square phi cos theta plus sin square phi cos theta. So therefore cos theta, if I take common, cos square phi plus sin square phi into cos square phi plus sin square phi into cos theta. Therefore cos theta will be remained. Cos theta multiplied by cos theta is cos square theta. Minus of minus, this will be plus sin theta. If I remove these two, multiply these two, cos square phi sin theta minus of minus plus sin square phi sin theta. If I take that sin theta common, cos square phi plus sin square phi is again 1. Therefore, sin theta remains. Therefore, cos square theta plus sin square theta, this will be 1. So, this integral, this determinant value is 1. Prior to that, I have r square sin theta. If I multiply this, ultimately I'll get r square sin theta. Therefore, what is the Jacobian of xyz with respect to r theta phi r square sin theta. Therefore, while evaluating the triple integrals, wherever you have dx, dy, dz, or dz, dy, dx, or whatever may be the product of these three, is to be replaced with, remember, r square sin theta, dr, d theta, d phi. Just to recollect you back, in cylindrical polar coordinates, this dx, dy, dz is r, dr, d phi, d theta. In polar coordinates, in two dimensions, the dx, dy is r, dr, d theta. In those two cases, you will simply get the Jacobian as r. Whereas in spherical polar coordinates, the Jacobian is r square into sin theta. This theta is the angle made by OP with the z-axis, the middle one. In the polar coordinate system, r theta phi, the middle angle, r square sin theta into dr, d theta, d phi. So once you convert from spherical to this, this is general procedure. Already in lecture 2 we learned. Once you are given as in one system, in Cartesian coordinate system, a triple integral is given. Replace x with what? Replace x with x is equal to r cos phi sin theta and y with r sin phi sin theta and z with r cos theta. And here, and if you simplify, ultimately this function will reduce to some function of r theta phi. So xyz goes out and we will get r theta phi. Dx, dy, dz is equal to r square sin theta dr, d theta, dz. As I said in the polar coordinates, cylindrical polar coordinates, here also, once you convert from Cartesian coordinates to spherical polar coordinates, remember that the region of integration here will not change. Both are same. So region of integration will not change in polar coordinates in 2 dimensions, in cylindrical polar coordinates in 3 dimensions, again in spherical polar coordinates in 3 dimensions, region of integration will not change. Reason is the polar coordinate system is another system of identifying the same point which is identified in Cartesian coordinates. If you identify a point in Cartesian coordinates, the same point you are identifying in another way. Method is different, but plane has not been, or space has not been changed. Whereas in general, if you take x is equal to some function of uv, y is equal to some function of uv in 2 dimensions. Similarly, in 3 dimensions, x as a function of uvw, y as a function of uvw, z as function of uvw. If you change, then the from xyz plane to uvw space, the space will be changed and region also changed in general. Okay, all these points are already discussed. So now let us evaluation of triple integrals changing to spherical polar coordinates. Let us see some examples. Before seeing these examples, I'd like to reiterate the most important point of it. Whatever region in space you have given, and there will be some origin. This is how we take the limits in the spherical polar coordinates. You just identify the region. In that region, you from the origin, you take some point and see the minimum value of R. Maybe from here, suppose this is R1 and this is R2. The R varies from R1 to R2. And there will be some z-axis here. See the in this region, if I take another point, if I take another point, here the least this is the angle theta what I get, and this is the if I take a point here, this is the minimum angle, this is the maximum angle. So the theta varies from theta 1 to theta 2. And take this projection, this region projection also on the xy plane. Some region you will have. In this region, observe what is the angle between those two. So this is the way to identify the to find out the limits. And okay, let us see the problems one by one. Example 1. Yeah. Evaluate double integral over r e power x square plus y square plus z square into root over this dv, as I explained in the lecture 4. This dv is also another way of representation for dx, dy, dz, where r is the region bounded by x square plus y square plus z square is a square, and x square plus y square plus z square is equal to b square. This x, you know that x square plus y square plus z square is equal to a square represents a sphere in 3 dimensions. In 2 dimensions, you have x square plus y square is equal to a square. Just in extension of that in 3 dimensions, it is x square plus y square plus z square is equal to a square represents a sphere. Similarly, x square plus y square plus z square is equal to b square is another sphere. A is less than b. A is the radius. So this is A. This is A, and this is B. And your region is bounded by these two spheres, means this region do not come into, this is the region of integration. So whatever I am marking here with red color, this is your region of integration. This is your x-axis, this is your y, and this is your z-axis. Okay, in this region, if how to take the limits? You assume that there is one sphere. Assume that two balls, one is inside the other. The center is the same for both. Through that center, imagine two balls, one inside the concentric balls. Imagine those two balls from the origin. Assume that there is one line going on. In between the two balls, there will be some region. That is your region of integration. So this is for finding the limits. First of all, I need to take a point here. That point I may take here, or I may here, or anywhere I can take in between these two. If I take this point here, the R value will be A. If I take the point here, R value is B. In between that, whatever point I take, R value will be in between A and B. Therefore, R limits are A to B. So where that R lies between A and B. Once this is over, then this is the z-axis. Say this is z-axis. I'll rewrite it because this figure is rotated a bit. So for your better understanding, I'm rewriting this. This is x-axis. This is your z-axis, and this is your y-axis. Or this I can call it as x-axis, this is your y-axis, and this is your z-axis. So this is A and this length is B, so R varies between A and B. Now, uh, what is the other R, theta, phi are the polar coordinates. In spherical polar coordinates, what is the equation of this sphere? It is x square plus y square plus z square is p square. X square plus y square plus z square is r square. R square is equal to b square. That means R is equal to b. The inner sphere is R is equal to a. So this is the equation of the sphere. Now this OP, whatever, suppose if I take a point here, this is the point P. This OP makes an angle, this angle. What could be this P? If the point P, this remember that this point P can be taken anywhere here. If I take the point here itself, This is OP, this is ZX, the minimum angle is 0. And if I take the point P here or anywhere on this, then the angle made by the ZX is pi by 2. Or if I take this here, this will be pi by 2. Or if I take this angle on the negative side of Z axis, and here the Z value will be pi. Therefore, this angle is always between 0 and pi for different points. So R varies from A to B, and theta varies from, yeah. So for this, for the first problem, R limits are from A to B and theta limits are from 0 to pi. As long as you are above the xy plane, you just imagine a line crossing through origin and above the xy plane, and the angle made by this z-axis will be from between 0 to pi by 2. If you come below the xy plane, then it is from 0 to pi. And next about phi. What are the limits for phi? It is very easy. Where that phi will be? Phi is the angle made by this OQ with x-axis. Where is that Q? Q is the projection of P on the xy plane. Now you need to take the projection of this on the xy plane. This is my xy plane. So this is xy plane. On this I am taking the projection. Projection of this entire one on this means from the below as well as from the above. I am focusing a light and on the xy plane. Where the image falls, image will be in this region. What is this region? The reason, sorry, that the image will fall in this region as well as in this region. If it is in this region and this is the angle made with x-axis, therefore this may be 0 and this may be back side of it, and also the angle made by this phi is 0 between 0 to 2 pi. So where that projection falls, so this may be here or maybe here, maybe here or maybe here. Therefore, this is origin. The angle made by this with these are all projections. All the with the x. This is your x-axis. The angle made is, if the projection itself falls here, the angle is 0. If the projection falls here, angle is pi by 2, or maybe backside pi and 2 pi, a complete circle. Therefore, phi will be in between 0 to 2 pi. You know r, theta, and phi limits in the region of integration. Now, what is your integrand? Triple integral. Let us see what the integrand is. E power x square plus y square plus z square into this. So everything is to be converted in terms of polar coordinates. In polar coordinates, what is x square plus y square plus z square? This value is r square. This is also r square. Root r square is r. You'll know what is dx, dy, dz becomes. Write all those things and put the proper limits. So e power x square plus y square plus z square, that is r square, root over x square plus y square plus z square, that is r square, dx dy dz becomes, as I mentioned, Jacobian is r square sine theta dr d theta d phi. Now r limits are from a to b and theta limits are from 0 to pi. To avoid confusion, I will write theta equal to 0 and phi limits are from 0 to 2 pi. I need to integrate it first. Remaining is an integration. Once you are thorough with integration, this part is easy. Otherwise, uh, you will find difficult in getting the answer. Even if you know the method, if you are not thorough with the integration, it will be a tough time for you to evaluate. E power r square, root r square is r, sine theta, dr, d theta, d phi. First, we need to integrate with respect to r. Now, if I put r square is t, 2r dr, 2r dr is dt. Therefore, to have 2, I'll multiply this by 2 and divide this by 2. So, half of, if I put r square as t, now I have e power t into another t, 2r dr will be dt. Now, e power t, this t, I will write it as t minus 1 plus 1. It looks like e power x into fx plus f dash x. The derivative of this is 1. E power x into fx plus f dash x integral is e power x into fx. For integral 0 to 2 pi, integral 0 to pi, so for t is my r square. So e power r square into r square minus 1. This is the integral for this. And I need to substitute the limits a to b. Sin theta is there. Integration with respect to theta is over. R is over. D theta and d phi are there. So this I am erasing. This I don't require here. Okay. Now substitute the limits. This is half of integral 0 to 2 pi integral 0 to pi. If I substitute the upper limit, e power b square into b square minus 1 minus e power a square into a square minus 1. This is anyway constant. From next step onwards, at the end I will replace it. This is simply some constant. I will call it as k sin theta d theta d phi. Now bring that k out. Therefore, k by 2 integral 0 to 2 pi. And now you need to integrate with respect to integral sin theta is minus cos theta. And we need to substitute the limits 0 to pi and d phi. 0 to pi cos pi is minus 1. So minus or minus will be plus 1. And if I substitute the lower limit, cos 0 is 1. Because it's the lower limit minus or minus plus pi, that so that it will be 2. So k by 2 into 2 and integral 0 to 2 pi d phi, that is phi. If I substitute the limits, that will be 2 pi. So 2 and 2 gets cancelled. Ultimately 2k means it is e power b square into b square minus 1 minus e power a square into a square minus 1. This multiplied by 2 pi. This is the first integral value. Now go into the second problem. Evaluate triple integral R dx dy dz where R is the region bounded by this. Now how do you know that this represents a, for this I here for the convenience of you people, in sphere equation, general equation is this x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus c equal to 0. Similarly, circle, this will have the center with minus u minus v minus w and some standard curves, standard surfaces. This is a sphere. This is center and radius is root over u square plus v square plus w square minus c. So this is the sphere, and of course, generally you don't get the general equation of a cone, general equation of a cylinder. Already in last class lecture also I have given you some hints. X square plus y square is equal to a square in 3 dimensions represents a cylinder. Cylinder of radius a. Cylinder of radius a. Axis is z-axis. Similarly, y square plus z square is equal to a square and z square plus x square is equal to a square. These two also represent cylinders. You just remember all that information. Similarly, a variable z is equal to root over x square plus y square. This represents a cone. But this x square plus y square, that means here I have z square is equal to x square plus y square. X square plus y square is equal to some constant square, that is cylinder. X square plus y square is equal to z square, that is cone. If only positive side is given, this is the cone. If you consider the negative side also, this entire one is this. Only this one is this. Z is equal to root over x square plus y square. And without square root, if I use z is equal to x square plus y square, this represents a paraboloid. This is paraboloid. I think you know the shape of this. This is paraboloid. This is paraboloid. Similarly, other things also you'll get. If you get y is equal to x square plus z square anywhere, then this will be the y-axis, and xz plane will be this. And similarly, x is equal to y square plus z. There are also paraboloids. Similarly, you have different cones here. The other than this, y is equal to root x square plus z square, x is equal to root x square plus z square are the different cones. Wherever you get such equations, these are the generally you will get these kind of equations. This information is a better one to know to identify the surfaces there. I suggest you to write these equations in a separate notes and remember what actually they represent and their shapes too. Okay. Coming back to our second problem, and this is a, if I bring this a here, z is equal to h by a into root of that. So this which represents a cone just now I mentioned. The h by a can be taken inside the square root also, ultimately this. Okay, and we need to evaluate this integral. And z is equal to h. Z is equal to h because the positive side only you are getting. So this is the cone what I got. And z is equal to h, we know that it represents a plane. This is z is equal to h. And this cone is az is equal to h into root over x square plus y square. And if these two intersect, you will have one circle here. You can observe a circle here. This is a circle what you have. Intersect. That will be there on this plane. So if I put z is equal to h here, h and h gets cancelled. And ultimately, what is that you will get here? X square plus y square is equal to a square. On this plane, you will have x square plus y square is equal to a square. So now what is your region? Region R is inside this cone. Here you have a cone. Inside that you have some region inside this cone. Now how to take the limits? As I mentioned, in this region you never go beyond this h because boundary is also given. So if I start here, you may take a point here which this may be your r. If I take the point here, this may be your r. If I take this point itself, this r is 0. So r is varying and it goes up to this. At this point on this plane, what is your r? Z is equal to h in polar coordinates. What it represents? Z we know it is r cos theta is equal to h. Therefore, what is your h? R is equal to h secant theta. So, the r value varies from 0 to maximum h secant theta. Therefore, what are the limits for r? R will be 0 to h secant theta. Now, if I have some uh, if I take a point here, whatever maybe here or whatever may be the point, this is the radius vector. This OP. It's making an angle. This is my z-axis. This is the angle. What could be this angle? What is the minimum? What is the maximum? If I take the point here itself, then theta will be 0. Or otherwise, where can I take the point? That point may be here. If I take the point here, this is the maximum angle what I get. Or if I take the point here, this is the maximum angle what I get. Therefore, what is the maximum angle? 0 to this. Now this angle I need to identify. For identifying this boundary is what? What is this boundary? This boundary is this cone. In this cone, in polar coordinates, what it represents? Az is equal to h into root x square plus y square is the equation Cartesian coordinates. Convert them into polar coordinates. A, z. What is your z? R cos theta is equal to h into what is x square plus y square? If you remember the Cartesian coordinates already at the beginning I have given you. So these are x and y. What is x square plus y square? If I square it, x square plus y square is r square sine square theta. I will get common. Cos square phi plus sine square phi is 1. So x square plus y square is r square sine square theta. R square sine theta is Jacobian. Here x square plus y square is r square sine square theta. So that is what x square plus y square is. So keeping that in mind, so x square plus y square is r square sine square theta. If I find the square root, r sine theta, r gets cancelled here. Sine theta by cos theta, that is tan theta. Tan theta is a by h, or theta is tan inverse a by h. So what are the limits for theta? Theta may be from 0 to this line. This is the equation of the cone in spherical polar coordinates is tan inverse a by h. Theta is equal to tan inverse, theta is equal to constant in 3 dimensions, represents a cone. Whereas in polar coordinates, theta is equal to constant in polar coordinates of 2 dimensions. Theta is equal to constant represents a line passing through the origin. Okay, theta varies from 0 to tan inverse a by h. So we got the limits for theta also. Theta 0 to tan inverse of a by h. Now, what is your phi? How to take the phi? Whatever point you take, you have to take the projection of them on the xy plane. So for that, I need to understand what is the projection of this entire region on the xy plane. Automatically, if I put a light above it, the projection means the shadow will be on this on the circular one here, because the same circle is the maximum portion that will come here. What is this? Already I found this is x square plus y square is equal to a square. So everywhere your projected point will be here. If I take the angle made by this with respect to x-axis, that angle may be this, or maybe this, maybe this, or maybe this. So it is 0 to 2 pi. So what are the limits for phi? Phi limits are 0 to 2 pi. I think this explanation is clear to you. So for this problem, for the second problem, R varies from 0 to but Z is equal to R secant theta, yeah. H secant theta, and theta limits are from 0 to tan inverse A by H, and phi limits are from 0 to 2 pi. And now he asked, evaluate triple integral, simply dx dy dz only he asked, where what region also he mentioned as the region between the cone, region inside the cone. So here r varies from 0 to h secant theta, and theta varies from 0 to tan inverse of a by h, and theta varies from 0 to 2 pi. This dx dy dz becomes r square sine theta dr d theta d phi, and integration is integral 0 to 2 pi. First we integrate with respect to r, 0 to tan inverse a by h. I think you remember that these are the limits for theta, and sine theta is a constant as long as I do the integration with respect to r. Integral for r square is r cube by 3. If I substitute the limits, h cube secant cube theta by 3 d theta d phi. So h cube by 3 is a constant which comes out sine theta into secant cube theta. Sine theta into 2 secant cube theta is, bring the secant theta 1 secant theta in the denominator so that it will become cos theta. Sine by cos tan theta into secant square theta will be there, 0 to tan inverse of a by h, and this is tan theta into secant square theta d theta d phi. Derivative of tan theta is secant square theta. Therefore, the integral for this is tan square by 2, that is h cube by 6 integral 0 to 2 pi, integral tan square theta between the limits 0 to tan inverse a by h d phi. If I substitute tan inverse a by h here, tan of tan inverse a by h is a by h. So ultimately h cube by 6, and here it is a square by h square, and integral d phi is phi. If I substitute the limits, that is 2 pi. 2 in 6 goes 3 times, h square goes h times, that way 1/3 pi h a square. This is something like 1/3 pi r square h. This is the volume of the cone. This is simply look like volume of the cone. What is this we see here? Go back to that figure. Yeah, this is the height from here to here. Because z is equal to h. This is h is the height, and this is the circle already I explained. This is x square plus y square is equal to a square. That means this is radius is a. So this is a cone of radius a and height h. Therefore, its volume is 1/3 pi a square h. Volume I got. What is that you have integrated? Have integrated. What is the integrand for you? Integrand is 1. So in a region, if you integrate 1, then the answer what you'll get will be volume of that. This is one application. Anyway, I'm going to discuss these things in my next lecture. Okay, so that is what your second problem. Coming to the third one, evaluate this. See here, if you for the time being you don't see that figure there, -2 to 2, minus root 4 minus x square to plus root 4 minus x square, 0 to this. This is the integrand what he has given. The previous two problems he described and he has given the what the region is, but here simply he has given a triple integral and he is asking to evaluate it not straight away but changing into spherical polar coordinates. So for doing it, unless and until you know the region, you cannot find out the limits for r theta phi if you convert that into spherical polar coordinates. Therefore, based on this, we need to identify the region. Now, from these limits, you can easily identify. Already I discussed these things in the first and second lecture. So these are the, because these are functions of x, y, therefore these are the limits for z. What are the limits for z he has given? Z is equal to 0 and z is equal to root over 4 minus x square minus y square. Can you tell me what this is? Z square is equal to 4 minus x square minus y square, or x square plus y square plus z square is equal to 4. What it represents? Which represents a sphere, but you have taken only the positive side. Therefore, above the xy plane, you have one sphere. That what this tells you. And where x and y, these are the limits for y. This is limits for x. Y is varying from minus root 4 minus x square to plus root 4 minus x square. That means x square plus y square is equal to 4. Your y is varying from minus root 4 minus x square to plus root 4 minus x square. These are the limits for y. And x square plus y square is equal to 4 means this is a circle of radius 2. X is varying from minus 2 to 2. Therefore, the y and x are varying on this projected region, which is a circle. So, you have a sphere. Now, from this, we can understand that you have a sphere. What is x square plus y square z square is equal to 4? That means it is a sphere of radius 2. And if you take the projection of the same sphere on the xy plane, you will get one circle. X square plus y square is equal to 4. Again, a circle of radius 2. X and y vary in this region, and z varies between z is equal to 0, that is xy plane to 6. So you are having set of all points inside the hemisphere. That is what our conclusion is from these limits. So here you have a hemisphere. hemisphere, the projection is this is your projection part, and Z is varying here. Now, as I said, in polar coordinates, this is my third problem. In spherical polar coordinates, what the surface, this is x square plus y square plus z square is equal to 4. That means r square is 4. This is r is equal to 2 is the equation of the sphere. R is equal to constant represent the equation of the sphere in 3D. R is equal to constant represent the equation of the circle in 2D. Remember all these things. If you, as and when it comes to your mind, you need to practice them. What actually the R is equal to constant represent. X is equal to constant represents what? In 2D it represents line. In 3D it represents plane. Like that. R is equal to A. R is equal to constant represents a circle or a sphere, depending on the dimensions you are taking. So this, if I take any point inside, this is my region or inside this, and also on the boundary. If I take R, if I take any point here, the minimum value of R is 0 here. If the point is here, maximum value of R is 2. Therefore, R varies between 0 and 2. Above the xy plane, I already mentioned it is easy to find out the theta. If the point is here, theta is 0. If the point is here, theta will increase. And if the point is here, theta value is pi by 2. Therefore, this is very easy to find out the limits for theta 0 to pi by 2. And what are the limits for phi? Phi limits are, what are the phi limits? I need to take the projection here. Depending on my point, the projection will fall anywhere. If this is x-axis, this is the angle, this is OP, this is x-axis. So depending on my projection may be in any point inside this region. Therefore, phi varies between 0 to 2 pi. You got the three limit. In fact, he has given minus 2 to 2, minus root 4 minus x square to plus root 4 minus x square, 0 to root over 4 minus x square minus y square. This is what he has given, and integrand is z square into root over x square plus y square plus z square dz dy dx. Now, if I convert this into spherical polar coordinates, I already z square is z is r cos theta, z square is r square cos square theta, x square plus y square plus z square is r square, square root of r square is r, dx dy dz is r square sin theta, dr d theta d phi, and r limits are 0 to 2, theta limits are 0 to pi by 2, theta limits are 0 to pi by 2, and phi limits are 0 to 2 pi. These are the phi limits, these are the theta limits, these are r limits. So we need to first integrate with respect to, I am straight away putting the integration values because you know how to find out this. The sine theta into cos square theta will be there. R square into r, that will be r power 4, r power 5. If I integrated r power 6 by 6, therefore it will be 2 power 6 by 6. And d theta d phi. If I integrate with respect to theta, cos theta, if I put t, minus sine theta d theta will be dt, so that it will be minus cos cube by 3 and 2 power 6 by 6 into 3 integral 0 to 2 pi cos pi by 2 is 0, and if I cos 0 is 1, so that it will be 1 d phi. So this is 2 power 6 by 6 into 3 into 2 pi. So these are the integral. I suggest you to do those integrations. 2 power 6 is 64 by 9 into pi. 64 pi by 9. This is the triple integral of that one. So from this is very easy to integrate. So I'm not spending much time on evaluation of those integrals. These are very simple, which you can integrate from your intermediate knowledge. I say, though, for those who have not thorough with the integration, again and again I am saying, first of all, concentrate on finding the integration. Otherwise, you cannot solve the problems easily. Coming to the fourth one, So again, he has given the limits and he is asking us to um, by solve this by changing to spherical polar coordinates. The students will really appreciate learning the spherical polar coordinates if they solve the problem straight away in Cartesian. If somebody try to solve this problem in Cartesian coordinates and then solve it by spherical polar coordinates, you can observe the easiness of this one. Okay. Now, what are the limits for z? Z varies from 0 to z is equal to root over 1 minus x square minus y square. If I square it, z square is equal to 1 minus x square minus y square, or x square plus y square plus z square is equal to 1, which is a sphere. That too he has given z is equal to root over 1 minus x square minus y square means only the positive side. And y is also from 0 to 1 minus x square. Y is equal to 1 minus root over 1 minus x square means x square plus y square is 1. X square plus y square is 1 is a circle, but he has taken from y is equal to 0 only. Y is equal to 0 to this. Only first quadrant he is considering here. And x varies from 0 to 1. X limits are this 0 to 1 and this is. So the projected region is falls here. When the projected region falls here, whenever in the space, if you take only the first octant. So for the fourth problem, this is he is considering only z is equal to 0 to this part, this xz plane, and this. So only this part. And if you take the projection, it falls only here. This is your projection. So this, if I write it separately, this is my x square plus y square is equal to 1 only in the first quadrant. This part is this figure. And this remaining part here, this is my region R. So as usual, if I take this 0 and this curve is x square plus y square by r is equal to 1, r varies from 0 to 1, and theta varies from 0 to pi by 2. As long as it is above the xy plane, theta value will be 0 to pi by 2, and phi also from 0 to pi by 2. Why 0 to pi by 2? If I take the projection that falls here, this is x-axis, this is the project, this is q, OQ, P is here, the projection is q, this is OQ, this is the angle that I am writing here. This OQ, this angle is, this is also 0 to pi by 2. So once you know these limits, then what he has given is 0 to 1. If you remember, this is 0 to 1, 0 to root 1 minus x square, 0 to root 1 minus x square minus y square, 1 by root this point I mentioned in the cylindrical coordinate also, here also I am putting here. Here you have x square plus y square plus z square. If I take minus 1 common, x square plus y square plus z square is equal to 1. That is the sphere what we have. We should not substitute x square plus y square plus z square is equal to 1 here. Whenever if you integrate 2 to 3 2 to 3 x square dx means x is taking the values between 2 and 3. Similarly, in this integrals also, xyz is a point inside the sphere. Inside the sphere, if I take a point xyz here, x square plus y square plus z square is not 1. X square plus y square plus z square is 1 on the boundary only. Therefore, we should not put x square plus y square plus z square is equal to 1 here. Okay. Now, r values 0 to 1, 0 to pi by 2. This is also 0 to pi by 2, 1 by root 1 minus r square, and dx dy dz is r square sine theta dr d theta d phi. So integration 0 to pi by 2. I will integrate only with respect to r. Remaining part you do it. I need to evaluate r square by root 1 minus r square. So I will write this r square as 1 minus of like this. 1 minus r square. 1 minus 1 and plus 1 gets cancelled is plus r square. So if I divide with 1 by r square, then you will have 1 by root 1 minus x square. Therefore, I can write this in this fashion. 1 by root 1 minus r square minus root 1 minus r square. This kind of simplification I did just to make this possible to integrate dr d theta d phi. Yeah. Now 0 to pi by 2, 0 to pi by 2, 1 by root 1 minus r square is sine inverse r minus, if I root 1 minus r square is r by 2 root 1 minus r square plus r by 2 sine inverse r. Root a square means x square, x by 2 root over a square means a square plus a square by 2, 1 by 2, a square by 2 sine inverse r between the limits 0 to 1. This is all between 0 to 1. Sine theta d phi. If I substitute 1 here, sine inverse 1 is pi by 2. If I put 1 here, this will be 0. Sine inverse 1 is pi by 2. Pi by 2 into 1 by 2, that will be pi by 4. If I substitute lower limit, this is 0, this is 0, that is 0. And sine theta d phi, 0 to pi by 2 here. This is also 0 to pi by 2. So ultimately, pi by 2 minus pi by 4 is pi by 4, which comes out 0 to pi by 2 sine theta. If I integrate, that will be 1. And integral d phi is 5. If I substitute the limits, that will be pi by 2. So that it will be pi square by 8. So this is the fourth problem. Next one is the fifth one. Yeah. This is also by changing to polar coordinates. Here, z is equal to root x square plus y square, z is equal to 1. So z is equal to root x square plus y square is a cone that already I have given you that. Z is equal to 1 is this plane. So this is, I'll write with, here I'll, and 0 to 1 minus x square. Remember, y is varying from 0 to 1 minus x square. That means, again in the first quadrant, y is equal to 0 to 1 minus x square. X varies from 0 to 1. So z is equal to root x square minus y square, z is equal to 1. This is a cone. This equation he has given as z is equal to root x square plus y square. If I convert that into polar coordinates, z is r cos theta is is equal to r sine theta. R square sine square theta, if I square root of r and r gets cancelled, sine theta by cos theta tan theta is 1, theta is pi by 4. Therefore, theta is equal to pi by 4 is the equation of this cone. I mentioned that theta is equal to constant represents a plane. So this is your x-axis, this is your y-axis. Here I have one plane. That plane is z is equal to 1. If a plane intersects this cone, you can clearly know that if a cone is cut by a plane, you will get this intersection is a circle. And that circle is, projection of that circle will be here on the xy plane. But he is not considering the entire circle, only first part of it. So as I did in the previous problem, this if I take any point here, theta varies from here to here. What is this equation? Z is 1. How do you know that Z is 1 from where you got? Z is equal to 1 is from this upper limit. Z is equal to 1. In polar coordinates, Z is r cos theta is equal to 1. That is r is equal to secant theta. So r varies from 0 to secant theta. If I point this, some value. If I take here, this is r. But if I take the point here, it is secant theta. If the point is here, 0. So definitely I am not going beyond it because upper limit is 1. Therefore, r varies between 0 to r secant 0 to secant theta. Theta is this, if the point is here, theta is 0. If the point is here, this theta is pi by 4. So theta varies from 0 to pi by 4. R varies from 0 to secant theta, and theta varies from 0 to pi by 4. And where the phi varies? Phi is the projected, where the projected region in the first quadrant. Therefore, what is the limits for phi? Phi is 0 to pi by 2. Once you know this one, you can easily, the double integral, what he has given, this is given integral. Integrand is 1 by root x square plus y square plus z square he has given dx dy dz, and this is integral 0 to secant theta 0 to pi by 4 0 to pi by 2, and 1 by x square plus y square plus z square is r square, that is r, and dx dy dz is r square sine theta dr d theta d phi. R gets cancelled here, and this is 0 to pi by 2. I think this is very integration is very easy. You can do it on your own. Integral r is r square by 2, that is secant square theta by 2. Secant square theta into sine theta. So sine by cos is tan theta into secant theta, that you can integrate and substitute the limits. Ultimately, the answer what you will, I am giving you the answer for it. Root 2 minus 1 into pi by 4 is the answer for it. You work out the remaining part. Okay, so this is for your homework. Okay, coming to the sixth problem, because integration is easy, I am leaving it for you. Once you have an idea, oh, this is good problem. Evaluate the triple integral over R, a region he has given which lying inside the cone and the sphere. X square plus y square plus z square is equal to, here this, it is not printed, it is okay, this is I'll write here, x square plus y square plus z square is equal to 6z. This print is not, this is it. So what is x square plus y square plus 6z is equal to 6z represent? If you compare with the standard form, x square plus y square plus x square by 2ux plus 2vy plus 2wz is equal to 0. If I write z quotient is 6, if I bring it on this side, this will be minus 6z is equal to 0. Therefore, the center is 0, 0, 3 is the center of the sphere, and it passes through the origin. So, it is the sphere is passing through the origin, and whose center is 0, 0, 3, which will be somewhere here. And z is equal to root 3x square plus y square is represents a cone. And the reason what he is considering is inside both of these. If I take the points here, it is outside the cone. So this is not my region. This is not my region. If I take the points here, this is also not my region because they are inside the cone but outside the sphere. So what are the common points there now? This is my region of integration is this entire part up to this. So if I start here, that I may take a point here and this R may vary from here to here. Now what is this R here on the boundary of this sphere? So you just imagine that in a ball you have inserted a cone, and inside the portion you are considering here. So what is the equation of this sphere in polar coordinates? X square plus y square plus z square is r square minus 6 r cos theta is equal to 0. R is equal to 6 cos theta. So what are the limits for r now? R varies between 0 to 6 cos theta. And if I take the point here itself, it is making an angle 0, and if I take the point here on the cone, vertex of the cone, then I'll get some angle. That is the maximum angle what I can make. So what is this cone now? This cone is z is equal to root over 3 times of x square plus y square. Z is r cos theta root 3 X square plus y square is r square sine square theta. That is r sine theta. R and r gets cancelled. Sine theta by cos theta, that is tan theta. Tan theta is 1 by root 3. That means theta is pi by 6. So the cone equation is theta is pi by 6. The minimum angle is 0 and maximum angle is pi by 6. Theta varies from 0 to pi by 6. And if I take the projection of it automatically, that is, this is the point of intersection of the cone, and here, if I, this is the circle, what you'll get, its projection will fall on the xy plane. Definitely, the projected region is a circle. What circle I don't require, because I don't require the range, only the angle we require. That is the beauty, that is the advantage of this method. And therefore, phi, I'm not interested in what that radius and circle is. Only circular region, that idea is enough for me. Phi varies from 0 to 2 pi. So these are the limits for r, theta, and phi. Therefore, he has asked triple integral z square dx dy dz. This is what he asked. This is in triple integral in polar coordinate 0 to 6 cos theta. R limits we know, and theta limits also 0 to pi by 6, 30 degrees, and 0 to 2 pi. Z square is there. R square cos square theta, that is z square. Dx dy dz is r square sin theta dr d theta d phi. Now integrate it. 0 to 2 pi, integral 0 to pi by 6, cos square theta sin theta is constant as far as r is concerned. R square into r square is r power 4. If I integrate it, r power 5 by 5. If I substitute the limits, 6 power 5, cos power 5 theta by 5, d phi, d theta d phi. So 6 power 5 by 5 is constant, and integral 0 to 2 pi, integral 0 to pi by 6, cos square theta and cos power 5 theta, that is cos power 7 theta into sin theta d theta d phi. Now this is 6 power 5 by 5, integral 0 to 2 pi. If I integrate it, minus cos power 8 by 8. Cos theta, if I put t, minus sin theta d theta is dt. So t power minus t power 7 dt, that is minus t power 8 by 8. If I substitute the upper limit, pi by 6, cos pi by 6, cos pi by 6 is root 3 by 2, root 3 by 2 whole to the power of 8 with a minus sign. If I substitute lower limit, cos 0 is 1, minus of minus is plus. So 1 minus root 3 by 2 whole power 8 by 8 t phi. So this is 6 power 5 by 5 into 8 is 2 cube, I can write, into 1 minus root 3 whole power 8 is 3 power 4 by 2 power 8, and d phi is 5 if I substitute the limits 2 pi. So you all know how to simplify it further. Simplify it, whatever you get, that is the answer. So ultimately, in today's lecture, what we learned is converting that to spherical polar coordinates. If you are given in Cartesian coordinates, which are given in terms of x, y, z, dx, dy, dz, replace them in r, theta, phi, and you will get some function of r, theta, phi, and it is r square sine theta dr d theta d phi. Evaluate double integral over r. How to take the limits for r? If I have this Cartesian coordinates and if I have some region, sometimes that region, the origin also may be here. You take this part, these are the limits for r, and this is the angle theta, and observe the minimum value and maximum value for theta, and take its projection. You will have somewhere else here, and take the projection of it. This phi, this angle is these are the limits, and these are the limits for theta and r. This is the procedure what we adopted. So with this I complete the evaluation of double integrals using by converting that to spherical polar coordinates. So in this unit 3, we are left with one more topic, that is applications of these double and triple integrals. That in these applications we learn how to find out the areas of plane regions, how to find out the volumes, how to find out the moment of inertia, how to find out the centroid, and all those things. For applications are very easy once you know how to evaluate a triple integral. So in these applications, what you learn is if you want to find out the area, what integral is to be evaluated for finding the integral. That integral will write and we evaluate. For evaluation, already in the previous lectures I have given, those things you have to learn. So by the time I start the next, I give the next lecture, I suggest every one of you to go through the previous 5 lectures properly. And once you are able to evaluate a double and a triple integrals, and if you can decide whether a change of variables or change of order of integration is necessary or not, by looking at that integral, you can easily apply those things for finding the volumes, areas, center of gravity, moment of inertia, etc., etc. So many applications.